Hi, welcome back. Today we're going to look at the intermediate value theorem and the squeeze theorem. Both of these are very useful in helping us to determine if we have intermediate values or if we can approach certain values from the left and the right. These are very useful, and you're going to see this on the AP, at least the IVT. So let's imagine we have this car here. And in this car, we are driving along the road. So let's assume that the x-axis here represents time, and the y-axis here represents our speed at any given time. The question I want to ask you is, how can we prove that at some time our speed was exactly 50? And most of you would correctly say, well, we're starting at 0 and we're ending at 100. So at some point in the middle, we have to cross 50. And that's exactly what the IVT says. I call it a duh theorem. But again, we just can't say something is true. We have to be able to prove it. So let's take a look at how we would prove this. So let's go down here. So we want to we must start with a continuous function on a closed system right here. So let's go ahead and draw a continuous function from A to B. So here's A, here's B, and I'm going to draw a continuous function right there. Now, the next part is also very important for us. We want to make sure f of A does not equal f of B. So this is important. So this is telling us that we do not want to start where we end up at. If I want to show that at some point my value is 50, and I start at 0 and end at 0, I can't guarantee I cross 50 at some time. And the next one, this is the part talks about the intermediate part. This is betweenness. Anytime you see something like this, we call it betweenness. Given that some y value is between f of A and f of B. So what they're saying is, if this right here is f of A, and that's where I'm starting, and I'm ending at f of B, that's a weird looking B. Still a weird looking B. That's a better looking B. Now, this is a y value that is between f of A and f of B. So it's just some random k value right there. Now, this is what the IVT says. If the function is continuous, and we're not starting and ending at the same place, and the value we want is between our two endpoint values, then we have to have that value of k. That's what it says. In other words, if the function is continuous on the interval a to b, then the value of the function at c must take on every value between f of a and f of b, given that c is in the closed interval a and b, a to b. So, and then we can answer it. Then yes. And then the answer would be very simple to write. Yes, the IVT will hold. And somewhere on our interval a to b, our function f of x will have to equal k. This is what we call the intermediate value theorem. If the function is continuous, and we're not starting and ending at the same place, and we have this betweenness, then the IVT must hold, and we must take on that value of k up here. So let's go back up here. I can do this. Yes, this graph is continuous, so we can say, yes, f of x is continuous on the domain 0 to 10. That's the first part. Yes, the value where I start is 0, and the value where I end at 10 is 100. They are not equal to each other. And yes, 50 is between my value at 0 and my value at 10. So all three conditions are met. So this says I'm continuous. There's no holes, no gaps, no jumps, no asymptote. I'm starting at 100 and I'm ending at 50, and this just says, hey, look, 50 is in between 0 and 100. So we can say, yes, the IVT holds, and somewhere on our domain, 0 to 100, the function, our speed, must be 50. So let's look at an example how the AP will ask these. Use IVT to prove that the function f of x equals x squared is 7 somewhere on this closed interval. So they're trying to prove that somewhere that the y value has to be 7 somewhere. So how can we prove this? Well, one, I could look at it. That's not too hard to graph. At 2, I know the value is 4 because it's a parabola. And at 5, I know the value is 25. Well, if I were to look at this, well, yeah, somewhere in the middle, 7 exists. So this has to equal 7 because we're going from 4 to 25. We have to cross 7 at some point. So let's go ahead and prove this using calculus. 1, is this function continuous? And that's what we're going to say. 1, f of x is continuous on the closed interval 2 to 5. You have to say that. 2, what's the value? I want to show that the value at 2 does not equal the value at 5. Well, what's the value at 2? Well, we just said that that was 4. What's the value at 5? 25. They're definitely not right. That's definitely true. And then our third step is to say, well, is 7 between 4 and 25? Absolutely it is. 7 is between 4 and 25. And that's it. That's all we got to do. So now we got to write our answer. Therefore, IVT holds, and somewhere on that domain, 2 to 5, the value must equal 7. Now, we can actually solve it. So we can actually solve this. We can find out where. Say, take a look. So, because take a look. If I were to graph it, there it is. Yeah, somewhere that value has to equal 7. So, could we find this point? Absolutely. If I take my function to solve, I can just take my function, x squared, set that equal to 7. So I get x equals square root of 7. You get two answers, plus or minus 7, right? You get plus or minus, but my domain is restricted to the positive, so we don't want the minus. We can just get rid of that one. We might be asked that too. So let's look at another example. Let f of x equal x squared plus x minus 1. Prove at some point the IVT holds through the interval 0 to 5. If IVT applies, find the rule value of c for the function. We'll deal with that later. So what they're trying to tell us is to show that that IVT holds. And to do that, we are going to use our rule. Take a look at this function. Is this function continuous? We're not asked to prove it. We just need to say, yeah, it's going to be continuous. There's no holes or gaps. So we can say, 1, yes, f of x is continuous on the domain 0 to 5. That's your first step. Step 2, show that the values aren't the same. F of 0 can't equal f of 5. If I try plugging that in, if I plug 0 in, I get negative 1. If I plug 5 in, what's that? 25 plus 5 is 30, minus 1 is 29. So if I think about this graphically, we're going from a negative 1 and at 5 all the way up to 29. Well, I don't know what this graph looks like, but it looks like this. We want to see if at some point the value will equal what? 11. So they're telling us our k value here is 11. Well, is 11 between negative 1 and 29? Absolutely it is. So the answer should be yes. And that's our third step. 1, 2, 3. That's our third step. 11 is between negative 1 and 29. So now we're going to answer our question. So therefore, and we're going to write it out, the IVT holds. The IVT guarantees that at least one time the value will be 11. The IVT holds, and somewhere, this is a sentence, on our interval 0 to 5, the value has to equal 11. And now the next part is a little bit, the next part, they're actually asking us to solve it this time. They're saying where. If it applies, find C. They want us to find the x value. So I can just do that. Where x squared plus x minus 1 equals 11, x squared plus x minus 12 equals 0. If I factor it, x plus 4, x minus 3 equals 0. I get negative 4, and x equals 3. But look at your domain. My domain is from 0 to 5. I don't want that one. I want that one, your domain. Make sure you check your domain on these. And there's our answer. All right, so take a pause for a second. Try number 3 here real quick. All right, we're back from your pause. So let's take a look at number 3. We want to show that this fraction the IVT hold through this interval. Now, it doesn't look like it would be continuous, but you're right. This would, so if I take a look here, it says, I know that x cannot equal 2. Well, when I look at my domain here, we run into a problem. 2 is between 1/2 and 7. Which, if you excuse me, looking back on my notes, I think I copied something wrong. That's supposed to be a 2.5. So let's go and fix that real quick. Okay, so let's see here. So we know that x cannot be 2. So now looking at it, 2 is within our is outside of our domain, so we don't have to worry about it. So we're going to prove IVT holds here. So first step, 1, f of x is continuous on our domain 2.5 to 7. I'm going to hear about that in my videos. I guarantee it in this chat room. 2, now I have to show that the value at 2.5 is not the same as 7. So I'm going to write this as 5/2, easy to work with that, does not equal f of 7. All right, plugging this in, if I plug in 5/2 here, we get, what's that? 1 over, what's 5/2 minus 2? That's 1/2. Does not equal, if I plug in 7, 1/5. So 2 does not equal 1/5. True that. So we're good. We proved it right. Step 3. Is 1/4 between 2 and 1/5? And the answer is yes. So we can say 2 is between 1/5 and 2. Whoops, not 2 is between that. That should be 1/4. Remember, our k value here is 1/4. Once we have all that, we can now answer it. Yes. So therefore, IVT holds, and somewhere over that rainbow, on our interval 2.5 to 7, the value of our function has to equal 1/4. That's it. Now, they do say to find where. So let's go ahead and find where this occurs. And again, we're just going to set your equation equal to k. That's all you have to do. 1 over x minus 2 equals 1/4. And if I solve that, yeah, x has to be, what's that going to become? Just 6 right there. You can kind of see that right there. What does x have to be to make that a 4? Pretty easy. And is 6 in our domain? Yep. This is in the domain that we wanted. Nice job, everyone. All right, so let's take a look at number 4 here real fast. So for a problem like number 4, it says, let the function be this. So this is a square root curve on a closed domain. So I know what this looks like from Algebra 1. So from pre-calc, we know what this looks like. If I start at 4, we know it's just going to be opening up backwards right here. That's what it would look like right here. So let's see if IVT can guarantee that at some point our value will be 1. So let's see here. 1. Is the function going to be continuous from -2 to 2? Yeah, I can see that. F of x is continuous on the domain -2 to 2. 2, I look at their values. Are the values different? F of -2 not equal to f of 2. Easy to plug in. F of -2 becomes the square root of 6. F of 2 becomes the square root of 2. They're not the same. That's what we want. And then step 3, we're just going to say, is my k value between them? Is 1 between root 2 and root 6? And of course the answer is no, this fails. 1's not between them. So this fails right here. We can't use IVT to guarantee it. So we can just say IVT fails, and that's it. Just fails. Okay? So anytime any one of these proofs false, it's just IVT fails. You don't have to do any more. All right. Oh no, Mr. Wernow forgot his calculator. That's insanity. But how can he show that the function here, natural log of x, has a root, or y equals 0, somewhere on the domain 1/2 to 3. All right, we're going to have to use logs here. I know what you're all thinking. Oh no, it's logs. They're bigger, better than bad. They're wood. All right, so our first step, 1, is the function continuous? We know natural log is continuous from soft bracket on this domain, so it's yes. So f of x is continuous on the domain 1/2 to 3. 2. Okay? I got to find the value at 1/2. And I got to make sure it's not equal to the value at 3. So I got to take the natural log. Ready? The natural log of 1/2 does not equal the natural log of 3. All right. Now, for those of you who may not remember, so let's think about the graph of natural log here. At e, the natural log of e, you remember, is 1. Is going to be 1. But the natural log of 1, insanity, of 1 is going to be 0. So I can graph my natural log. It looks like this. There's my natural log graph. So take a look here. Anything between 0 and 1, anything on the domain 0 and 1 is less than 0. So I don't know what the natural log of 1/2 is, but I do know that this is going to be negative. And a negative does not equal a positive. There you go. A negative number can't be a positive number. And it's not much of a proof, but without a calculator, I really can't do much else but just know what it means. And then the third step, well, now I have to look at my 0. Well, that's my k value. So what we're saying is, between 1/2 and 3, do we cross the x-axis? And that's what we're saying here. Is 0 between a negative number and a positive number? And yeah. So therefore, yes, IVT holds. And somewhere on our domain, 1/2 to 3, the natural log of x has to equal 0. That's the best thing, and that's why we like IVT. I can't solve it like up here. See, up here, I could solve it. Up here, I could solve for it. Up here, I can solve for it. But down here, I can't solve for that. So we can use our IVT to show that, hey, look, I may not be able to know what the answer is, but I know it exists. All right, let's try this one. Show that sine of x equals negative x takes on the value 0.5 on the interval. Same idea. So there's my, whoops, sorry, that happened. That happened again. There's our k value. So I can do this. I'm going to write this as a function. Write this as f of x equals sine of x plus x there. Makes it a little bit easier to work with. And then I'm going to do step 1. Is the function continuous on that interval? Yeah, sine's continuous. F of x is continuous on the interval 0 to pi over 2. 2, I got to show that the values aren't the same. That's easy. What's the sign of 0? 0. 0 plus 0. Sign of pi over 2? 1. 1 plus pi over 2. There we go. So 0 does not equal 1 plus pi halves. Perfect. They're not the same. 3, whoops, step 3. Now I want to say, well, is my value 1/2 in between 0 and 1 plus pi over 2? And the answer is definitely yes, right? Yes. Yo, that's definitely true. So therefore, we can do our answer. Therefore, IVT holds, and somewhere on the interval 0 to pi over 2, the function f of x has to equal 0.5. That's it. That's the IVT right there. So come back in the next video, we'll take a look at what we call squeeze theorem.